Okay, can you all hear me?
Yes, sir.
Start off with this question here. So we start off with the worked example. Sorry. So here I think first of all, let me just start the recording. I will periodically start the recording and stop because most of the time I'll be giving you all time to
Recording in progress.
Okay, so this is the slide where I have included the simplified hybrid pi model, right? So here is on top we have the original, the complete hybrid pi model, complete with C mu, R mu, right? And R naught. And we are able to eliminate R naught because it is large compared to the 1 over R simple E, right? We can also eliminate R mu because it is very large, right? And we can approximate it to an open circuit, and we can break down to the Miller capacitance for the input and the Miller capacitance for the output, right? So from that, we end up with, right? We take the Miller capacitance for the input as Ci, right? And the Miller capacitance for the output as Co. So Ci will equal how much? C mu divided by 1 minus AV. Co will equal minus AV C mu divided by 1 minus AV, right? So here we have the simplified hybrid pi circuit, right? The simplified hybrid pi circuit, right? So it's there in the slide that I uploaded. So 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 we're talking about the values of worked example 4. Now we are going to use these values, and so previously we found the high pass frequencies, or in other words, uh, the cutoff frequencies due to the bypass capacitors, the bypass and blocking capacitors. Now we will look at the low pass cutoff frequencies of the amplifier that occur due to the parasitic capacitors, right? Or in other words, the high frequency analysis of the amplifier. So now we're going to try this question over here, right? So here, the resistor values are the same as worked example 4, right? C pi is given as 20 picofarads and C mu is given as 10 picofarads, right? Okay, so now you can give you about 5 minutes to attempt this on your own first.
Recording stopped.
Okay, so I've paused the recording for now, so you can now make an attempt. Okay. So this is the common emitter circuit. Oh, sorry. Let me start the recording.
Recording in progress.
Okay, so this is the common emitter amplifier that we were talking about. So again, the emitter is bypassed, right? So we are talking about the high frequency. We're talking about the high frequency circuit. So obviously the RE which is bypassed, right? Short circuit, right? All of the blocking and bypass capacitors are short circuits. And the transistor is the hybrid pi model, right? So first of all, right, we have to use the T model, right? Using the T model, we have to find the gain of the transistor, right? We have to find the gain of the transistor. Sorry, we have to find the gain of the amplifier. So AV is going to equal, because this is a bypassed common emitter, RC parallel to RL divided by R simply. So from the previous result, right? So from the previous result, you can calculate RE, right? So RE is 4.9, right? RE is 4.9, right? And the gain is, we previously calculated this to be minus 185, right? So now what we have to do is, first of all, we have to calculate the Miller capacitances, right? So because I calculated these values before, right, I'm not going to spend time again, but later on when we do other examples, I will do it. Actually, yes, for this I haven't given because I mean it's based upon the values that we got from worked example 4, right? That's why I haven't given the thermal voltage here, right? Is that clear? We got the results we calculated that in class, right? Worked example 4, we did that in class, in our previous class. So I'm using the values that I used for that. So the gain is minus 184. First, what we have to do is we have to calculate the Miller capacitances, right? So first, the Miller capacitance for the input, right? The Miller capacitance for the input, which is going to be what? C mu divided by 1 minus AV. So that is 10 to the power 10 times 10 to the power minus 12 divided by 1 minus 185. So the answer we get there is a very low value, which is 5.3. We are taking as 5.36 times 10 to the power minus 14 farads or 0.05 picofarads, right? So it's a very small value. 0.05 picofarads, right? It's a very small value. Then for the output Miller capacitance, that is minus AV C mu 1 minus AV. So that is minus 185 times C mu 10 picofarads. Forgive the divided by 1 minus 185. And the answer we get there is approximately, right? It's around 9.9 picofarads, right? So because of course, right, these two are very close, approximately 10 picofarads, right? Doesn't matter, you can straight away take it as 10 picofarads, right? So those are the two Miller capacitances. Next, let's calculate take a screenshot here. Next, let's calculate the okay. Right, so now what we have to do is we have to calculate the cutoff frequencies for each capacitance, right? So again, we are going to use the relaxation circuit, right? So that, let me clear this. The relaxation circuits. So we have the, let me draw the C pi plus the input Miller capacitance over here. And here we have right, here we have R pi. Here we have C pi plus the input Miller capacitance, which is very small, right? And here we have GMVBE times the output Miller capacitance, which is approximately 10 picofarads, right? This is very small, so when taken in parallel, this will be approximately equal to 20 picofarads. So for the output, the resistance of the relaxation circuit will be RC parallel to RL, right? For the input, we will have a further RS parallel to R1, parallel to R2, and then that will also be parallel to R pi, right? So from this, we get for the input 2 pi times the equivalent resistance RS is 70 parallel to 33 kilo ohms. I will write it as 33K for short. 10K parallel to 490, right? R pi is beta times RE 100 times 4.9, therefore 490. So this is approximately equal to 69.2 ohms, right? Approximately equal to 69.2 ohms. So as I mentioned, it is the source impedance that determines this relaxation resistance, right? So 69.2 ohms times 20 picofarads, and the frequency that we get, the answer that we get is 114.6 megahertz, right? You'll get something close to 114.6 megahertz. For R out, this is straightforward, right? It's very simple, right? RC is 1 kilo ohm, RL is 10 kilo ohms, and then there is approximately 909 ohms. The capacitance is 10 picofarads, 1 over 2 pi times 909 ohms times 10 picofarads, and the frequency you get over here is 17.6 megahertz. 17.6 megahertz. So out of these, the cutoff frequency is the lowest, right? The cutoff frequency is going to be the lowest out of the two. Why? Because here we have 17 megahertz, here we have 114. So here is the mid-band frequency. The roll off will start at 17, right? It will start at the first critical frequency is going to be 70 megahertz, right? So this will be an additional roll off. Okay. And finally, the transition frequency or unity gain frequency right? The unity gain frequency over here. So it's going to equal how much? 1 divided by 2 pi C pi. Okay, so there's a question here. Do we have to memorize all of the gain equations? The answer is no, right? The answer is no, because you will be asked the question in a way that you will have to derive it. Okay? You will have to, in the exam, you will be expected, you won't be expected to memorize any of this. Instead, you'll be given the circuit, right? And based on that, you will have to derive. Okay? And don't worry, for the mid-semester, it's open book, right? The mid-semester evaluation will be open book. Okay. So C pi, right? 20 picofarads. So always be careful about substituting the units, because that is one of the commonest mistakes that you make. R is 4.9. Then approximately this will equal, right, 1 gigahertz, right? This will be approximately 1 gigahertz. Okay. So now there is another question that I have given, right? There is another question that I have given, right? But as I can remember, I have not asked the transition frequency for the exam, right? And also, this kind of equation, right? I mean, this anyway, you do not have to memorize this kind of equation, right? Don't worry about that. Because this is anyway not a, anyway, the transition frequency you do not need to calculate in real life. It will be given to you in the data sheet, right? You don't have to calculate it by yourself, right? So this is just given for the sake of an exercise. Yes, how to calculate RE. Yes, RE, we'll get back to that, okay? RE, because I'm going to do many more examples. So in a suitable example, we will calculate RE, right? Okay, so there is one more example in the slides that I have given, right? So here, this is what I mentioned in our last lecture, right? So now you're given a bandwidth, right? You're given a bandwidth, and then you're expected to find the necessary values of the capacitors, right? Here you're given the bandwidth. Now, before you were given the capacitor values, right? The capacitor values were given. What you have to do is find the critical frequencies, right? You have to find the critical frequencies. Now, right, the bandwidth is given. You have to find the capacitors, right? Right. So I will do a very simple similar example that is given in the past papers, right? I will not do this one. I will do a similar example in the past papers. So now let's move on to the last year's mid-semester exam, right? We'll move on to last year's mid-semester exam first. Yes, reference book I will mention, right? I will, yes, I will give you all a couple of reference books. I think the best one is Floyd's book. I will post a few possible reference books on Moodle, okay? Okay, so now I have uploaded this on Moodle. This is the okay, so the question is in the early one, don't we have to calculate the cutoff frequency of the bypass capacitor and why are they low pass, right? That also I will, when we discuss the next question, I will talk about that, right? Okay, so as you can see, this question here, right? So first we will now, okay, so some of your questions I can understand, right? So you asked how to calculate RE and that type of question. So this question will, right? Question number 1 of the previous mid-semester exam will answer that question, right? So here, right, HFE, remember, is beta, right? I haven't done hybrid parameters this year because, as I mentioned, it's not a very, it's a somewhat obsolete method, right? HIE is another term for R pi, or in other words, beta times RE, right? So here we will calculate RE. So for anybody who hasn't, who is not familiar with the calculation of RE, we will do it in this example. Okay. Right. So in this question, for the fixed bias bipolar junction transistor amplifier shown in figure 1, right? VCC is 5 volts, right? VCC is 5 volts. RB is 390 kilo ohms. RC is 1.2 kilo ohms, right? If VT is 25 millivolts, VB is 0.7, and VCE is 2.9 volts. We're supposed to calculate, right? Don't worry about this. We're supposed to calculate number 1, beta, right? A, we're supposed to calculate beta. B, we have to calculate R pi, or in other words, beta times RE, right? And C, the precise value of HOE. HOE is R0, right? It is R0, right? So R0, also we learned, it is equal to the early voltage plus VCE. Sorry, I'll write it over here for clarity. The early voltage plus VCE divided by IC. Okay, right. So here, right, we'll use the T model. Yes, we'll use the T model to determine these values. Okay. So first of all, let's draw the circuit T model. Here is RE, right? I give my diagram. So here is the constant current source IC. Here is RE, and we will calculate this value for the student who asked the question previously. We will calculate this value here, VCC, and this is grounded. Sorry, RC here, RB over here, right? So first we have to calculate beta, right? So we'll take this current I capital B and this current IC, the collector current IC. So IB VCC is equal to RB IB plus VBE. IB is equal to VCC minus VBE divided by RB. 5 minus 0.7 divided by 390 kilo ohms, right? And the answer we get is leave it blank for now. And then IC, here we have given VCE is given, right? So VCC equals RCIC plus VCE. VCE, right? IC will equal VCC minus VCE divided by RC. That is 5 minus 2.9 divided by 1.2K. And then we get the answer. So IB is 11 microamperes, right? I hope you all also got the same answer, right? IC will be 1.75 milliamperes, right? Then beta, you divide the two, times 10 to the power 3 divided minus 3, 11 times 10 to the power minus 6. Beta is going to equal approximately, right? The precise answer is 159, approximately 160, right? So that is beta 160. Next, RE, right? So for the student who asked, RE is equal to VT divided by IE, right? VT divided by RE, where VT is the thermal voltage, right? So here we'll approximate it to VT divided by IC 0.02, it's given as 0.025 divided by 107 1.75 milliamperes, right? 0.175, and then we get the answer. Okay. So RE, the answer for RE is 14.2, right? 14.2. So to find R pi, we multiply the two and then we get the answer, which is 2 point, approximately 2000, 2.2 kilo ohms, right? Approximately 2.2 kilo ohms. So RO is VA, yes, so given that also. So the early voltage is 50. VCE is given as 2.9 volts. Divide that by 0.0175. Here, of course, don't worry about the approximation. You may approximate it as 50 divide. You may approximate this straight away to VA divided by IC, no problem. Yeah, divided by so the answer you get is approximately 30 kilo ohms. Okay. So remember, this is the assessment, and last year also it was open book, right? This was open book. Okay, so do you have any questions or clarifications? So now you can try the second question, right? So for the student who asked, you can try to derive them, right? If you know how to derive them, then that is fine. So now you can try question number 2. So don't worry about these notations, right? HFE, HIE, right? As long as you know HFE is beta, then that is enough, because that is given in the because that you will have to find because usually that is the value for beta that is given in the data sheet, right? So HIE is R pi, right? HOE is R0. Don't I mean those are the values, but don't worry, because anyway we haven't done it. So Okay, so let's move on to the next question now. So here you're given the circuit, right? So remember, right, you don't have to memorize anything. All you need to know is the method of analysis, right? Number one, first rule, no need to memorize equations, right? No need to memorize equations, right? What you need to know instead is how to derive them, right? So always the circuit will be given, right? So you can see over here, the circuit is given, right? The circuit is given. And here, right? Okay, so we'll do this. This is not a very difficult question. So we'll get the AC circuit. So when we are getting the AC circuit, and when we do it for low frequencies, T model, right? So constant current source, RC, right? This is grounded. Here we have R simple E, right? Here we have R2 grounded. And here we have R1 grounded, right? So, sorry about that small, I have to make small correction here. So here we have RE, here we have R capital E, right? The input capacitor, output capacitor, and the bypass capacitor. So here, in this particular example, right, ZS is not given, right? ZS is not given, right? So anyway, when you connect it to the source, you can assume that it is negligibly small, right? This is not given. So what is the method for deriving the equation, right? We take each capacitor, right? Ci, Co and Cb. We take each capacitor as it is, right? We take each capacitor. When we take, for example, the capacitor, we want to find the resistance, then we open circuit the other two capacitors, right? We open circuit the other capacitors. So we open circuit this, and we open circuit this too. Sorry, this has to be connected across. This has to be connected across the load. Right? It has to be connected across the load. So we'll start off with C1, the input capacitor, right? So in which case we short circuit the source. We short circuit the source. And then what do we get for the resistance? We have R1 is grounded. So that means R2 and R1 are in parallel, right? R2 and R1 are in parallel. This current is IB, right? But this current is IE, right? So there is a break in the current, right? There is a break, there is a discontinuity in the current. We have to now relate IE to IB in some way, right? We have to relate IE to IB in some way, right? So IE will approximately equal IC, which will approximately equal beta times IC, right? So from that, sorry, beta times IB. So from that IB, right, sorry, right, beta times IB. So now we can rewrite this as the capacitance here, R1, R2, and now beta times R simple E plus R capital E. All these are now in parallel. So Ci, the relaxation circuit resistance will be R1 parallel to R2 parallel to beta times Re simple E plus R capital E. Right? So Cin is given as 10 microfarads. Right? It's given 10 microfarads. Then for C out, right, straight away the relaxation resistance is RC parallel to RL. For CB, that is the difficult one, right? That is the difficult one again. So we have RE, and here also we have IE going through here, but IB going through here, right? So this is open circuited. This is open circuited. So we have RE parallel to simple RE plus, right? Now this is IB if we take it as, if we want to rewrite this, then this is in terms of IE, this is IE divided by beta, right? IE divided by beta. So RE plus R1 parallel to RE parallel to simple RE plus R1 parallel to R2 divided by beta. Right? So likewise, as long as you can derive these circuits, then you are safe. Right? As long as you can derive the answers, then you are safe. Right? So here, now the important part in part B, we have to calculate the high pass frequencies. We have done that before. Now we are given, right? We are given the high pass frequency of 20 hertz, right? Here we are given the high pass frequency of 20 hertz. So what do we have to do here is we have to first calculate the, right? We have to first calculate the relaxation loop resistances. We first calculate them and then we find the capacitance for the given cutoff frequency, right? We find the capacitance for the given cutoff frequency. Okay. So now what do we do? We have the respective relaxation loop impedances R1 parallel to R2 for C in parallel beta times RE simple E plus R capital E, for C out R C parallel to RL, for C bypass it is RE parallel to R simple E, R1 parallel to R2 divided by beta, right? So let's calculate these values. We'll quickly calculate these values now. So ZS is 0, right? ZS is 0. So let's calculate the values now. So for C1, so sorry, C in, $39K parallel to 12K parallel to 100. So RE is given, RE when we calculate it is 5.7. So here when you calculate RE, right, remember you have to, the easiest way to calculate RE, oh, I'm sorry, yes, thank you for pointing that out. So sorry. This is, sorry about that, so sorry about that. Right, okay, sorry about that. Right, so here when you're calculating RE, right, so we are not, I mean, this, what we do is we take this point, right? The easiest way to take to do this is to take R1 and R2 as a potential divider, right? That's the easiest way. So we calculate Vx, right? We calculate Vx as R2 divided by R1 plus R2 times VCC. So that will be, right? So you don't have to derive the, I mean, for this kind of problem, you can straight away take this as a potential divider, right? So that will be, Vx will be 2.8 volts, and then Vx will equal VBE plus R capital E IE, right? 2.8 equals 0.7. RE is 390 times IE. And from this, we can find IE. Right? 0.5 milliampere. And then we divide that by 25, right? We divide that by 25. And RE will be VT divided by IE. 0.025 divided by 0.05. RE will straight away be approximately 5 ohms, right? So that is how you find RE in that case, right? Okay, so R is 5 plus 390. Approximately this will equal approximately 7.5 kilo ohms, right? Or for the input capacitor, Ri will equal approximately 7.5 kilo ohms, right? For the output capacitor, right, are 1.2 plus 5 plus 39K parallel to 10K divided by 100, and that will equal 77.9, approximately 78 ohms, right? This will equal approximately 78 ohms. Okay, so now we are given the cutoff frequency as 20 hertz. Now we have to find the suitable values for the input capacitor, the output capacitor, and the bypass capacitor, right? The input capacitor, the output capacitor, and the bypass capacitor. So we'll start off with the value of Ci. Now that will equal 1 divided by 2 pi f cutoff times Ri. So this is 2 pi times 20 times 7.5K, and then the value that we will get for this is 1, right? Approximately 1 mu f, right? The answer we'll get for the input capacitor is approximately 1 microfarad. For the output capacitor, 2 pi 20, which is the cutoff frequency, is 20 hertz, right? Ri is 11.2 kilo ohms, and the answer that we get here is 0.71 mu f, right? 0.71 mu f. So here, right, we have to write this in terms of a practical value, right? We have to write this in terms of a practical value. So what we want to do is, right, when we can either go to the one that is higher than this, which is 0.82 mu f, or the one that is lower than this, right, which is 0.68 mu f. Out of these two, which option are we going to choose, right? Out of these two, which option are we going to choose? Okay. Okay. So the answer will be the larger one, right? The answer will be the larger one. As one of you mentioned, it is the larger one. Okay. So to explain that, now another one of you had asked about the how to get this, right? So before, the cutoff frequency for a given relaxation circuit, right? C, we'll take this as C simple I and R simple I. For a given relaxation circuit, the cutoff frequency FC is given by 2 pi R1 RI CI, right? That is the cutoff frequency, right? So we want this to be 20 hertz, right? We want this to be 20 hertz. So that means the cutoff frequency must be either 20 hertz or less than it, right? The cutoff frequency has to be either 20 hertz or less than it. So if we increase C, right? If we increase C, then we are going to decrease the cutoff frequency. So if we increase C, then we will end up decreasing the cutoff frequency. So out of the two practical values, we have to go for the higher value, right? That is correct, right? That is the correct answer. So for the output capacitance, for the output capacitor, the value will be 0.82 microfarads. Okay. So now one of you had asked, how do we get this value, right? How do we calculate this value 0.71 mu F? I will explain that for the bypass capacitor, right? So we'll take the bypass capacitor, right? Critical frequency will be the relaxation circuit. Here we have the bypass capacitor. Here we have the equivalent resistance R. We'll take it as RB. Right? So the cutoff frequency will be 2 pi times RB times CB. Right? So for the student who had asked that question, right? The student who had asked the question as to how we get the capacitor value. Now, initially what we did was we were given the capacitor value. We calculate, we find out through our analysis, we find out the resistance value, right? And then from that, we calculate the cutoff frequency, right? From that, we calculate the cutoff frequency. In this question, what we are doing is we find, right? We find the equivalent resistance, this, and we try to find the capacitance for a given cutoff frequency, right? So in this question, what we are doing is the cutoff frequency is given, right? The cutoff frequency is given as 20 hertz. We find the equivalent resistance of the relaxation loop of the relaxation circuit. We find that, right? And in the case of the bypass capacitor, the equivalent resistance is 78 ohms, right? Now the cutoff frequency is given, RB we have calculated. We need to find the value of the capacitor to give us this cutoff frequency. Is that clear? For the student who asked that question? Is it clear to you now? Yes. The resistance values are the previous ones. Yes. In the case of, choosing the greater value for the larger practical value, right? In the case of choosing the larger practical value, yes, the resistance value is the same, right? The resistance value is, this resistance value remains as 1120 ohms. Okay, right. So now we have the cutoff frequency. We are trying to find the capacitor for the value for the bypass capacitor, right? The value for the bypass capacitor that will give us a cutoff frequency of 20 hertz. So now CB will equal 1 over 2 pi 20. The cutoff frequency is 20. The equivalent resistance is 78 ohms. This will give us a capacitance of, right, 102 microfarads, right? 102 microfarads, right? 102 microfarads. So here also the same problem, practical values 120 microfarads or 100 microfarads. We want to reduce the cutoff frequency. So in that case, we go for 120 microfarads. Okay. So as I mentioned in class also, the bypass capacitor, right? The bypass capacitor is different to the other two capacitors, right? The input and output capacitors which block DC are in series, right? But the bypass capacitor is in parallel. So because of that, the required value for the bypass capacitor is very large, right? Compared to the other two, it is very large. And also, as I mentioned, capacitance, right? Increased capacitance will also increase the cost, right? Increased capacitance will also increase the cost. So because of that, we have to choose must choose the lowest values, the lowest capacitance values, right? This is important. Must choose the lowest capacitance values. Okay. So now the answers are 1 CI is 1 microfarad, C out is 0.82 microfarads, and the bypass is CB is 120 microfarads. Okay. So now we can try part, right? Now we can try part D, right? Now we can try part D, right? So here, of course, there is a small problem. There is a small mistake in the question. Okay. So the question is here, why do we not go for the high? But we go for the higher value here too. For the student who asked that question, here, the answer that we get is 102 microfarads, right? Out of, so that means we can either go for 100 microfarads or 120 microfarads. Out of those two, we go for the higher value. Is that clear? Right. Okay. So here, of course, there was a small problem in the question, right? Here I have, so here we are supposed to find the value of the base to emitter capacitance that will give us a cutoff frequency of 20 kilohertz, right? The value of the base to emitter capacitance that will give us a cutoff frequency of 20 kilohertz. And here, of course, I have given the source impedance, right? Because it is necessary, I have given the source impedance. So some students had taken, when calculating these values, had taken the source impedance as well. Don't worry, in either case I had given marks, right? In either case I had given marks. So, right? Of course, it was my mistake when it came to making the question, right? So this is a bit different from what we have learned so far, right? I've straight away said neglect these two values, right? Straight away said neglect these two values. Okay, so we'll come to this now. Right? So for this particular question, right? For this particular question, now the hybrid pi model, we have R pi, right? The C, the input Miller capacitance, right? Plus C pi, right? The current source, GM VBE, right? This is the base, this is the emitter. And here we have the output Miller capacitance, right? Here we have the collector, and here also the emitter, right? So we saw how, right, when we derived the circuit, we got R1, the Thevenin equivalent Thevenin resistance, R1 parallel to R2. Sorry about the messy drawing, right? Right. So we saw how we get R1 parallel to R2 parallel to RS, right? RS, which is the source, right? Which is parallel, which is the source resistance. Right? So we also have R pi in parallel now. And now here we have the input Miller capacitance plus C pi. Right? So this, now in our previous example, we saw that for the given values, this gave us a very high answer that is in the order of megahertz, right? We saw how the answer we got for this is in the order of megahertz. So here we have a requirement, a cutoff frequency of 20 kilohertz, right? A cutoff frequency of 20 kilohertz. Now these capacitances are very small, right? These are in the order of picofarads, right? So, and these, and we also saw that the most influential resistor is the source resistor, right? So if we take the values, right, if we take the high pass frequency values, then our cutoff frequency, right, if we take the relaxation circuit values, it will approximately be Ci plus C pi, right, which will be, in the previous example, it was 20 picofarads, approximately 20 picofarads, and Rn, right, this will become approximately Rs, right, which in the previous example was 70 ohms, right? So if we substitute these values, then we are going to get a cutoff frequency that is in the order of megahertz, right? We are going to get a cutoff frequency that is in the order of megahertz. But we want a cutoff frequency that is 20 kilohertz, right? That is 20 kilohertz. Many orders of magnitude smaller than the cutoff frequency due to the parasitic capacitances. So what we have to do to achieve that is we have to connect an external capacitance between the emitter and the base of the transistor, right? And for the student who asked about the emitter, right? Remember, at low frequencies, right? At mid frequencies, right? At mid frequencies, we assume that all uh, blocking and all uh, coupling, blocking and bypass capacitors are short circuits. So CI, CO and CB will all be considered as short circuits, right? This is in the mid-band frequency, right? The mid-band frequency range. So when we go to high frequency, anyway, these are short circuits, right? Because the reactance of a capacitor is omega C, right? So if at mid-band frequencies, this is approximately equal to 0, when omega increases even further, this will go even, this will get even lower, right? So we can anyway, we don't have to worry about for at high frequencies, we don't have to worry about this bypass capacitor. We can straight away get rid of this. Okay, I hope that answered your question, right? So to lower the cutoff frequency, what we do is we connect an external capacitor like this, right? We call this the external CBE base to emitter capacitor, right? We connect an external capacitor, right? And we are neglecting these two, right? We are neglecting these two values. So we'll take it as C capital BE. We'll take it as C capital BE, right? So we are anyway assuming that this is very large compared to C pi and C mu, right? So we can then neglect these two. So then what we get is, we get our input source impedance parallel, right? Our source impedance and the other, right? Source impedance parallel to R1 parallel to R2 parallel to R pi. And here we have C, our external capacitor. So now if we get the value of this, the value of all of these in parallel will be so R pi will be around 500, so that will be 100. Sorry about that. I got a bit of a small technical issue. But is it called a low pass cutoff frequency because below that frequency we neglect the parasitic capacitances for our analysis? No, 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 no. That is not the reason, right? That is not the reason, right? The question is it called a low pass cutoff frequency because below that frequency we neglect the parasitic capacitances for our analysis? No, it is not called because of that reason, right? So as I mentioned before, right? Now, let's take our amplifier response, right? So we have our low frequency cutoffs, right? For our low frequency analysis, we get what is called a high pass frequency, right? That is because above the high pass frequency, the gain is the output, right? Above this frequencies will go through the amplifier, right? Below it, we will have a filtering effect like that, right? And these high pass frequencies are determined by the DC blocking and bypass capacitors. The parasitic capacitances, right? They will act as low pass frequency, cutoff frequencies, right? They will act as low pass cutoff frequencies. Anything below them, we will have a response like this. Anything above it, there will be a roll off like that. So the low pass, right? Here, the blocking capacitors and the bypass capacitors, they make the amplifier act as a high pass filter. While the parasitic capacitances, C pi and C mu, will make the amplifier act as a low pass filter. Is that clear? Is that clear to the student when I ask the question? Right. So to explain this, what we are doing here in a different way, so we select the values of our blocking capacitor so that we have a lower cutoff frequency of 20 hertz, right? We have a high pass cutoff frequency of 20 hertz, right? And if we were to take our parasitic capacitances, then the low pass cutoff frequency will be in the order of megahertz, right? So the natural or the cutoff frequency due to the low pass cutoff frequency due to parasitic capacitances will be in the order of megahertz. This is too high for our requirement, right? This is too high for our requirement because we want it to be 20 kilohertz. So what we have to do is we have to reduce this to 20 kilohertz like this, right? So this will not work with the parasitic capacitances. It's not going to work with the parasitic capacitances. Instead, what we have to do is we have to connect an external capacitor CBE to the base and the emitter of the transistor, right? And then we have to calculate the necessary value to make sure that it gives you a cutoff frequency of 20 kilohertz. Okay, so I hope that's clear, right? So now we have the relaxation loop capacitance is CBE, right? It is CBE, which is larger, many times larger than C pi and C mu, right? It's many times larger, right? It's very large compared to C pi and C mu. So because of that, we neglect C pi and C mu. And here, the equivalent resistance in the relaxation loop for the equivalent resistance for the relaxation loop will now become RS parallel to R1 parallel to R2 parallel to R pi, right? So it is the same, it does not change. So value wise, we have 100 ohms parallel to 39 kilo ohms parallel to 12 kilo ohms parallel to R pi, which is approximately 500 ohms, right? R pi is approximately 500 ohms. So this will give an equivalent resistance of 83.3 ohms, right? Approximately 83.3 ohms. So now the capacitance, the needed capacitance is CBE. It's going to equal 2 pi times the cutoff frequency, which is 20 kilohertz, right? 20 kilohertz times the relaxation loop resistance, which is 83.3 ohms, right? So now we can find the value, right? Now we can find the value, right? So let's calculate the value. Yes, the question is how do you get 500 as the value of R times pi, right? You get that because beta is if RE, right? RE is approximately 5 ohms, right? For the student who asked that question, why do we get the value of 500? RE is approximately, we found it to be approximately 5 ohms, right? And beta is 100, so 500. Okay. right? So the answer that I get is approximately, the answer that I get is approximately 0.96 microfarads, right? The answer that I get is 0.96 microfarads for CBE, right? So now the question is, are we going to increase it or decrease it, right? Are we going to go for so the larger value will be 1 mu f, the smaller value will be 0.82 mu f, right? So here, remember, this is a low pass filter, right? This is a low pass filter. So we want the cutoff frequency to be, right? We want the cutoff frequency to be, the cutoff frequency to be the frequency that so this has to be higher than, right? If L has to be higher than 20K, right? It has to be higher, right? Not lower, right? We want it to be higher. So in that case, we have to go for the smaller one, right? Remember, because this is a low pass, then we go for the smaller one. If it is high pass, we go for the larger one, right? So previously we went for the larger one because it's a high pass filter. In this case, we are going for the lower one because it is a low pass filter, right? So remember, right? High for the high pass filter, low for the low pass filter, right? Keep that in mind, right? So the answer will therefore be 0.82 microfarads, right? That is because it is low pass, right? Okay. So I hope, right? Okay. Any clarifications regarding this? Right? Any clarifications? Okay. So now we'll move on to the last year's final exam paper, right? The question in the, we'll look at the question in last year's final exam paper. Right, so here's the paper. Okay, so here you can see I've given a question like this, right? I've given a question like this, right? And VT is given, right? So that means that, right, you have to be able to derive the input impedances, but when it comes to RE, you should know that it is VT divided by IE, right? RE, this you have to know, right? This you have to know. So this is one equation that you have to memorize, right? And it's not very difficult also, isn't it? Right? So here you can see I have given the external capacitor is already given, right? It's already given to avoid any confusions. Okay. So this is a very similar question, right? It's a very similar question, right? So don't worry about question 1, right? Don't worry about question 1. So here, right? I mean, don't worry about question 1 because anyway, like these will all involve the use of hybrid parameters. So you don't have to worry about that. This year we don't have those, right? But this of course is not that difficult, right? You can find the mid frequency gain, right? So here you can see this is a fixed bias, but there is an emitter, right? Emitter resistor, so it's an emitter bias, and the emitter is bypassed, right? The emitter is bypassed. So what happens here is that the gain here also, because the emitter is bypassed, the gain that you will get will be, right, minus RC parallel to RL divided by R simply, right? So this is a common emitter amplifier, but it is fixed emitter bias, right? Fixed emitter bias, and it's the emitter resistor is bypassed. So here VC is given as 2.3 volts, right? VC is given as 2.3 volts. So from that you can calculate IC, right? The idea is that you can calculate IC because VC is given, right? And from that you can calculate RE, right? You can calculate RE. The input impedance, right? That is this input impedance. It's going to simply be, right? R, if we short circuit this, it's RB parallel to beta times RE. Yes. Thank you for asking that question, right? So, I mean, I will focus on the common emitter, right? Don't worry. I mean, the common base and the common base and common collector. I mean, frequency. I'm not going to do the frequency analysis for those, right? So for this, you only have to look at the common emitter, right? Only the common emitter amplifier, right? And you recall there is a reason, right? There is a reason why we only do the common emitter, we only do the frequency analysis for the common emitter amplifier. That is because we can easily get rid of the parasitic, the base collector parasitic capacitance using the Miller theorem, right? So don't worry too much about the frequency analysis of the other two, right? We will focus on the common emitter only, right? So here also you can see it's a common emitter amplifier. So here the output impedance, right? The output impedance, the input impedance and the output impedance is simply RC parallel to RL, right? The rest of this question, don't worry, right? Don't worry about the rest of this question. You can try the second question, right? And I will also upload the Python program where you can give a cutoff frequency. You can calculate the capacitor values, or you can also give a cutoff frequency and find the respective values. You can do either of those, right? I will upload that also, right? And I plan to give your mid-semester exam on the 11th of September, right? I plan to give it on the 11th of September, that is Thursday, the Thursday just after the mid-semester break, during the 1:15 p.m. slot, right, during the lecture slot itself. So the mid-semester will be 1 hour, right? It will be 1 hour, right? 1 hour online assessment, right? It will be open book. And I will post the details on Moodle. I will post the specifics on Moodle. So tentatively, right? This is still tentative, right? I will confirm. Once I confirm all of these details, I will post it on Moodle, right? I will confirm with Dr. Pranjeevan regarding the availability of that slot, and then I will post the details. And remember, right? The final exam is closed book, right? The final exam will be closed book, but the mid semester will be open book, right? Right? The mid semester exam will be open book. Okay, is that clear to everybody? So remember the mid semester will be open book, but the final exam will be closed, right? That is mainly because now typically in an open book exam, right? Most students wait until the exam to study, right? They think that, they'll be able to find all the answers open book, right? So because of that, generally, students make more mistakes in open book exams compared to closed book exams. So because of that, the final exam will be closed, right? Okay, right. So if you have any further clarifications, yes. Actually, yes. Yeah, because right. Yes. Sorry about this. I know there's a bit caused a bit of a. Yes, the question is this: why don't we buy? Why don't we open circuit the bypass capacitor for the input impedance, right? So yes, I agree, right? So we can also take the input impedance. If we do not bypass the the emitter resistor, the input impedance will be simple RE plus capital RE, right? The reason why I have given the answer like this is because for this particular question, right, the hybrid parameters we generally consider it for the case when the emitter is bypassed, right? So that had to do because this is actually the question related to H parameters. So if we are considering the mid-band frequency, right? I have mentioned that in the previous question, right? The mid-frequency gain, right? If we are considering mid-band frequencies, then we can straight away bypass this, right? Or else if we are not considering RE as being bypassed, then this is the answer, right? It's going to be RB parallel to beta times R simple E plus R capital E. Okay. Exactly. I hope that answers your question. Oh yes, the reference book is Floyd, right? But I will, post a few more good books, right? I will post them as soon as possible. If I don't post them on Moodle by Friday, can you please remind me? Right? Just remind me in case I don't post them by Friday. I will do it by Friday. Okay, I'll do it as soon as possible. Okay, any further questions? Okay, so if you have any further questions, you can ask me at any time, right? You can, my contact number, I think most of you have it. 538-433, right? You can contact me over WhatsApp on this number, right? And right, email, I mean, email is also fine, but the only thing is that, you know, because I get a lot of emails, a lot of spam, I sometimes might miss your email, right? So if you send me a WhatsApp, it's I'm more likely to respond to it quickly. Okay. Right. Okay. So I think the time is now 9 o'clock. We'll stop it. Right. And then Monday, the 8th of September, you will have the lecture as usual. And then for that, we'll start a new section. Right. We'll start a new section on operational amplifiers. Right. So you won't be examined on operational amplifiers. Right. You'll be examined up to what we have done. You'll be examined on what we have done up to frequency analysis, right? Okay. Right. Okay. That's it for today. Right. And you won't be having the lecture on Thursday as well, right? I think Dr. Pranjeevan also will not be taking the lecture, but if he's taking the lecture, he'll let you know, because I mean we cannot. It's unlike, I mean, he'll let you know as soon as possible, because I cannot take the lecture at that time because of the staff meeting. So that's why I had this session online today. Okay. You're welcome.
Recording stopped.